A very good morning to all of you. In the last class, we had just started with hardware flowcharts. Today, we'll see a little more details about how to make hardware flowcharts for various instruction sets. Right. Let's first again revisit the rules of operations. We said, there were a few rules of operation. So this was the basic ALU which we assumed we have. And based on this basic ALU, we framed some rules of operation. So one was a transfer from source to bus and destination takes one state time, and a source can drive up to 3 destinations, right? So this was one of the important rules. Simultaneously data could be transferred from one source to up to 3 different destinations. So that was one. And also we assume that this ALU out here, so let me take a pointer. We said that K, there is an K input available to the ALU, where K can take the values of 0, +1 and -1. Okay, so this was one more rule which we had set. Okay, and then we said whatever the ALU computes, okay, it computes data between two registers. Okay, the output would be available in T1 register. Okay, and then from T1 you could transfer to any of the registers. So whenever in the first step, an ALU will be given two data, either from two registers or from one registers, and then it could be K also. So either two registers or one registers and K, and the output would be available in T1 register. So that was another rule which we had adopted. And then when we say the transfer of AO activities, that is whenever a data needs to be transferred to the memory, what we do is we place the memory location, address of the memory, in the AO register, address output, and we put the data into the DO, okay, data out. So whenever we need to write some data into the memory, the corresponding memory address is put into AO and the data is put into DO. And whenever we need to read some data, so we put that memory address again in the same AO register, and then the data which is to be read will be available in the DI. So these were some of the rules which we had set. So based on these rules, we started making the flowcharts. So we said first we saw level 1 flowcharts, and then we said level 2 flowcharts also, in which the housekeeping task was merged with the operation task, okay, in the level 2. So for example, here if we recall, if we have to transfer a data, okay, from RX, if you have to add the contents of RX and RY, and then and also finally the result has to be in RY, right? So that this is the way we write it. So how to make a flowchart is this indicates it's an register to register operation. Add indicates that the ALU, the control word needs to be given to the ALU, add control word, okay, that is to be given to the ALU. So first we said there are two bus, right? If I go back here, there are two bus, A bus and B bus. So from the contents of RX is written into the ALU through A bus. Contents of RY register through B bus is written to ALU. Okay, so now the result of this will be available in the T1. Right now, in the next cycle, the result of the T1 is transferred to RY. So that is what what was desired out here, right? Parallelly, we need to also prepare this for the next cycle. So in this case, if you see here, the contents of the program counter through A register, okay, is brought to the AO and also to the ALU. Okay, so once it is brought to the ALU, to the AO address output buffer, right? From that memory, whatever data is written, so that is brought into the instruction fetch register. Okay, now what happens is that the next instruction is being while this activity is happening, right? The next instruction cycle is next instruction that requires to be decoded is parallelly being brought, like this T1 is being transferred to RY. So parallelly you have this A bar A bus free, right? So what you are doing is you are using that from the that bus to prefetch to place the address of the next instruction and then fetch that instruction into the instruction fetch register. Okay, and also since we have placed the like we said, the contents of a register can go up to 3 destinations. So we have also placed the contents of PC into ALU and increase the and also place +1 into the ALU. So what it does, it is going to increase the count of the PC. So in the next cycle, what happens is, if you see here, the contents of now ALU, whatever was the contents of PC, that has been increased by 1, and that is available in T1, because here if you see PC contents is placed in ALU and +1 is placed. So now what you get in PC is PC +1, right? So the count of the program counter has been increased. So that and then so that now we have prepared it for the next cycle. So before we finish off this cycle, we have incremented the value of the PC, so that in the next cycle when an execution operation task is being executed, then parallelly the contents of the PC will enable to fetch the next instruction. So that is the reason we are increasing and making available the PC with data for the next instruction, right? And obviously then this was prefetched already, this into the IRF. So from the IRF it is going to the execution. So from the fetch it is going to the execution. So this is how of register to register transfer a flowchart would look like. And then we also saw how an register to the memory flowchart would look like, right? Here again, so because the instruction is RX, the contents of RX needs to be added with contents of a memory whose location is given by RY here, right? So it is not contents of RY, but the contents of some memory whose address is given by RY, and the final result also needs to be stored in that memory which is given by the contents of RY. So the first step is, since it is a register to memory operation, so we write a register to a memory out here, right? And then since it's an add operation, we are going to write an add out here, right? Okay, having done that, now what we can do is like first the contents of PC through the A bus bar is brought to the address and to the ALU, and then you are putting +1 also to the ALU. So the moment you have put this address of PC into AO address, okay, the contents of that memory is brought into the instruction fetch register. So the next instruction is being fetched out here, right? In the next instruction is being fetched, and the program counter we are trying to increase the count out here. So we have done +1 here. Now this +1, so now the program counter you have the incremented value in T1. So that through B you are getting it to through the program counter. Okay, this should be A, I guess, right? Okay, through you can get it to PC, right? Now if you see here, once it is the new address has been brought to P. Now the contents of an RY register is brought to the address. Now because we have to add the contents of this memory, right, given by RY. So now RY is being brought to AO, And also whenever we do a memory operation, we said that address is temporarily stored into an T2 temporary register also. This also was one of the rules which we had set. So now the moment we do this, this is written in an alphabetic order. So actually after this is done, the contents of from the memory will be brought into the DI register, right? Input register, because you have activated the address with the contents of RY. So that particular memory has got activated. So whatever is available in that memory will come into DI. But this is written in an alphabetic order. So this happens first and this happens first. But because this starts with E, it is written on the top, and this, since it's starting with R, it is written in the bottom. But all these things happen in the same cycle. That is why it is put in the same box. And also since an output and bar is activated, so we have put a box out here. I guess there should be a box here also, because you have an AO output and data bus being activated here also. So there should be a box out here also. Okay. Now if you have see this contents of that memory is already available in DI. So now we can go ahead and do the add operation. So from DI through B it's brought to ALU, through RX it is again brought to ALU. Now they will get added and it will be available in TY. So from the TY, now again this data needs to be returned back into the memory location, right? So it is through A you can place to DO out, okay, data out register, and now you also have to specify the address where it is to be returned. Now we had saved the contents of RY in T2 register. We said that every time an memory address decoding is done, the memory is stored in T2. So from T2 you are placing it to address out. So whatever the result of the sum of those two, which was given to ALU, is available in TI, and that data is placed in DO. And simultaneously the address from RY which was stored in T2 is again put into the AO. So this is how this level 2 flowchart for add and register to memory is written out here. Okay. So let's now let's take a feedback on the execution unit design. Now if you see here, this was the instruction which we had written, right? Earlier we studied. So RX data from RX used to be added with RY, and the result needs to be in RY. So this is the one which we read. Now if you see here, both the registers and both the internal bus A and B both have been used here simultaneously. Okay. So when we make a flow chart, we also come to know that here also, see, both the bus have been used simultaneously, right? So once we write these flow charts, we can tell that okay, there is a requirement of 2 flow charts. So initially we assumed, okay, we require an ALU which has got 2 flow charts, right? Which has got 2 internal bus. Now when we are making the flow charts, and we can see that in many occasions both these things are required. So that means okay, so at least this is the, if we don't have these 2 bus, then the number of cycles required to do this operation will increase. Like this is simultaneously these operations are happening, right? From register to it is coming to ALU through one bus, and through the next register through B bus it's coming to ALU. Now if you have a single bus, right, then this will have to be split into, so it will take that much more time for the execution unit to perform this task. Okay. So seeing the flow chart, we are able to tell the requirements for the execution unit. Okay. That is, 2 bus are required. Okay. And hence we can optimize the design, right? So if you am for some particular purpose, if there is a requirement of more than 2 bus, then you can specify it. You can see that requirement in a flow chart, Similarly, for say you are doing very small program where there is no requirement of 2 bus, that also can be seen in an flowchart. So here that's what the flowchart gives an feedback on execution unit design. That's what we are saying here. Now, for example, now if you put that there is only one flowchart here. Okay, if you assume that only that there is one in which the output can be transferred only to one location, right? If you put that constraint, another constraint, what from PC the data was being transferred to AO as well as an ALU, right? So if you see, and that is the reason this could happen in 3 steps, right? Now suppose if you put an constraint that you cannot do that, okay, it can be transferred to only one location. So you will see this from the PC, it cannot it can go to only one location. Sorry, this has to be ALU. This will be okay, ALU, right? So so now if you see here, the number of steps required is more, like 1 2 3 4 steps are required. That means it is going to take more time for execution. So that is why now this will give, since we are assume that output can be transferred to more than. So this is one conditions we have set, which has enabled us to make an more compact in a flow chart. Okay, so so this is how the flow charts decides the kind of hardware requirement. Okay, that is what it says. Like whatever assumptions we make in a flow chart, that actually results in hardware implementation, right? So that is the way the hardware will be implemented. Right, so they are closely related to each other, the flow charts and the hardware aspect. Okay. Now similarly for an controller design. Now if you see here, if this is the instruction which we wrote for AND, right? So if you have to write it for sub, or if for subtraction, or for AND, or for OR, okay, the sequence of these events will be same. Right, so all the housekeeping task will be same. Only thing what will change will be the instruction which is given to the ALU, right? So if you see here, this was the ALU which we discussed. Okay, only the input which is given here to the ALU, whether it is going to decide whether this ALU is going to do subtraction or addition, or an AND, or an OR. Okay, rest of the things is same, right? So if you go back here, now if you see here, so when for an add, subtraction, and OR, only thing which changes is the instruction code which is given to the ALU. Rest of the housekeeping task and all these things, okay, they remain the same. So how do we write and design a controller? Okay, so whenever you have an instruction set, okay, we write only one sequence for each instruction independent of the registers. Okay, so if you do that, suppose there are k instructions, right? If there are k instructions like AND, or subtraction, colon, and and there, so we write one code each for decoding this. So that particular control word to the ALU needs to be generated, right? So you write an code for separate code for AND, or odd, subtraction, and so on. And then the address modes. Okay, so there will be different address modes, right? For register to register, irrespective it is AND, add, or add, subtract, and or, the housekeeping task will be the same. So we can make one program. Okay, we can write one code for register to register transfer, right? Similarly, for register to memory, I can write a different code. So the instruction set is split into two now, right? So one is for the op code. Okay, you write a program. So that is for different and or operations there can be k different types of codes. Okay, the purpose of this decoding operation will be to give the ALU the command whether it is and or subtract or something. And the second code which we are going to write is for the for decoding the address. Okay, that is whether it is a register to register operation or register to memory operation or register to base plus displacement. So you can have a different kind of addressing modes, right? So you have k different types of operations and a different kinds of addressing modes. So you can make actually you can write k different codes for decoding the opcode, and you can write a number of codes for decoding the address. And then you can whenever an instruction is fetched, then you can make any combination from k and a. You can take whatever is required from the k, from the set of k, and one from the set of k and one from the set of a instructions, and make the required instruction, right? So that is how we make the controller design out here, right? Okay, this we said like for addressing mode, right? Like for addressing modes, if you see from register indirect, okay, that means if the contents of the this is just the address mode sequence, right? Now how to make the code for the address mode. So register indirect means, like for example, the contents of ry needs to be fetched. So how do we do that? So we put ry into B, contents of ry through B bus into AO and T2. So the contents of simultaneously, the moment the address bus is activated, the data available will be through the address bar, it will come into the DI. So this is register indirect. So this is what I said, we make this a different kind of instructions, right? So the K is for add and subtract. So these kind of instructions will be made for the operation code. Now we are talking about the address modes for register to register indirect. So this is the kind of instruction which will be written. Okay, this is only decoding the address part. Okay, so this is only that part of the program, right? Similarly, I can have a base displacement. Okay, here what it is being done, if you see here, the contents of the program counter is brought to address and to the ALU also, and you are increasing the contents of the you are adding +1 also, so that the program counter in the next cycle it is in increased. Okay, simultaneously what is done out here, if you see here, so in the next cycle from T1 it is placed into the address bus. So once you do this displacement value, which is there in the code, okay, that is available in some memory in the instruction code, right? So that is the reason we are putting that the new value of the program counter into the AO. So this will be brought into the ALU register in the next cycle. Okay, and then contents of RY is also brought into the ALU register. So what we are doing is we have to generate this memory location RY plus 5H, right? So 5, this is the displacement which has been given. I am just giving an example. So so RY first in the ALU RY is brought here, and where will be this 5 available? It is available in the code, right? So that code needs to be brought. So how to get that is through the PC, right? So whatever is the contents of the PC is brought into the into the AO register. Okay, through the ALU. By first you are increasing the contents of the program counter and putting that into the PC +1 count into the AO register. So that will now indicate indicate the location where the program is written. Okay, in that program it will be this displacement will be written, right, whatever it is. So that has been brought into the ALU, right? So once that has been done, now from the T1 register again we are putting it okay, back to AO register and also to the T2. So once this it is brought into the AO register, so from the external bus it is brought into the DI. So this is how a base plus displacement program is written out here. Okay, we'll take more examples so things will be clear, right? Similarly, I can have a branching instruction, right? Branching instruction is whenever we write a program. Suppose we set a counter. So if the counter value say it comes to 0, then you write jump to 0 to some memory location, right? Okay, jump to 0 means we are doing some arithmetic operation. Say we have a counter and we are writing, okay, decrement the count, and if the count is 0, then you jump to suppose you have to do some addition of n number. So you put that n into one counter, and in every loop you keep decreasing the count value. So the moment the count comes to 0, you are going to you have to jump out of that loop, right? So that is the kind of instructions in 8086 also. You might have learned how to write those kind of programs, right? So this is like Z means 0 flag, Z is equal to 1 means, okay, Z is equal to 1 means 0 flag has been set to 1. Okay, that means that 0 condition has been met, and then you have to jump to RY. So how to write a flow chart for that? So in this case, what we are doing is, if you see the contents of RY, okay, where we have to jump, that is brought to ALU out here and to the address out register, right? And then now the contents of RY is available in AO, and you are also putting +1 to the ALU. And also you are giving the contents of RY into an ALU. So the moment the address bus is activated, okay, from that address bus, okay, the next wherever we want to jump, okay, that instruction will be brought into the IRF out here. Okay, now suppose that so there could be two cases, like this is happening parallelly when some computation is happening here, right? Now if the result of this computation, it could be the Z flag can be still be 0, or it could be set to 1. Suppose the 0 flag is set to 1. Okay, in that case what happens is, what we need to do is, now if you see here, this data has already been fetched. So from the fetch data, that is the next step which is to be done, right? Because you had already put RY into AO. So straight away now RF will be contents of RF needs to come into the execution, and also now the program counter needs to be updated with an RY, right? So here the contents of RY, right, and +1 you have done it. Okay, so our contents of RY is being brought to RF, but the program counter needs to be updated, right? So we had put +1 also into the ALU. So the contents of RY +1 is available in T1. Now that is being so the program counter is being updated. Now you have jumped to some other location of the program, and it will start executing with the new program counter. Suppose it is not 0, like if the 0 flag is not set. Okay, Z is equal to 0 doesn't mean it is 0. Z means Z flag. Okay, Z is equal to 0 means 0 is not this condition is not met. Okay, so then you come back. Now you have to see again, then there is no program counter need not be updated, right? So because there is no jump here. Here means there is no jump here. Now so again program counter value is again brought to ALU and to AO. So now so this data which was brought in IRF, okay, this needs to be updated. So this was corresponding to the jump 1, so that needs to be updated. So hence you are putting because there is no jump here, so the contents of program counter is through A bus, it's brought to ALU and also to AO, right, address out buffer, and then accordingly this is a normal sequence, so that data which is available corresponding to the PC is brought into IRF out here, right, and then you are giving +1 to the ALU to increment the count of the PC. So again from once this IRF is data is brought into the instruction fetch, in the next thing it is going to instruction execute mode, and from T1 because you have increased the contents of the PC, so that is now it is being updated. The PC, the program counter is being updated with +1 here. So this is how an branch instruction will be, and the flowchart for the branch instruction looks like. Okay, here what we have done is we have assumed that we have taken RY and then brought RY is the position where if the jump if the 0 condition is met, then I need to jump to the location specified by RY. So I have taken this as the I am assuming that it might jump, and then I have made this, and then if it is jumping, then I go ahead with that, and then if it is if there is no requirement of jump, then I am updating again, I am reverting back the data with the contents of the PC. So I can do it the other way around also. Here if you see here, the contents of PC is put into the ALU as well as to the output. So it is the normal sequence. Okay, whatever is the IRF, the next IRF is brought here, and +1 to the ALU. So in case there is no jump required, then obviously from IRF it comes to IRE, and then from T1, because you have already increased the contents of the PC, so the PC contents will be updated with +1 here. So this is the normal flow. So in case 0 is encountered, that is the 0 flag is set, and then you make an additional set of instructions out here, branching instructions, in which now the contents of RY is being placed through the A into the ALU and AO. So now into the instruction fetch, a new instruction which is given by RY is brought out here, and then also you need to set the PC program counter with so this data was now has become redundant, because now you are making a branching operation. So if you see here, you are putting a +1 here to the ALU, and then from T1 you are getting it into the PC. So now the PC you have a new data which is available, right? And from the IRF you go to the execution, from the fetch register to the execution register. Okay, so these two both are doing the same thing. Only thing here in the previous slide what we discussed was first you are taking the contents of an RY, okay, assuming that it might jump out here. Okay, here we are assuming that the probability of jump is lesser, so we are doing this instruction first. So depending on the what actual instruction and how do you want to program it, so you have both the options available for branch instructions to write the flowcharts. Okay, so let's again revisit some of the rules for doing level 1 instruction. Look, it is first assumed that the IR is done in the previous instruction itself, right? So IR is assumed to contain, because in the beginning of the instruction, right, the fetch instruction is already done. Like in the previous instruction, the program counter from using the value in the program counter, the instruction is already fetched and it is available in IRF. So when I start a flow chart, so the first thing I will do is from instruction fetch to I get it into IRE. Okay, so that is one assumption so every instruction towards the end has to finish the instruction fetch for the next instruction. Okay, and in the next instruction IRE, it will start with IRE. Okay, and then so this is one assumption, and then instruction begins with address mode sequence. Okay, so once we see some examples, this will be clear. And for when we make a flow chart for add and sub n, they are identical. Okay, so all the housekeeping functions will be identical for all these operations. Only on the top of the box you need to write an whether it is add and subtract or something like that, so that the hardware engineer knows that, okay, in the flowchart it is indicated that this is the operation which requires to be done by the ALU. Otherwise, if the addressing mode changes, then obviously the housekeeping task changes. So as long as the addressing mode remains same, okay, for these instructions, okay, they all remain the same. Okay, so we'll see a few examples, then it will be clear. Okay, now let's talk about register to register transfer. Okay, we are only talking about register to register transfer. Now if you see here, here the contents of RY needs to be transferred to RX register. Okay, so how do we write a flow chart for that? Okay, so this happens parallelly. It is going to remain same for okay, this remains same, like from the this is the housekeeping task. This remains same for all of them. From the program counter, it is brought to through a bus, it is brought to ALU and to the AO. Okay, so once it is the address output buffer is activated, so the data which is available in that memory is brought into the instruction fetch register. So for each instruction, this is being done for the next instruction and not for this particular instruction. So this housekeeping task is clearly for the next instruction. Okay, and also the instruction fetch register, from the instruction fetch register, it will be brought into the instruction execution registers towards the end of this cycle. Okay, so this is the next task, and from now the count of the PC has been increased. So we are starting with bringing the data from the now whatever was the value of the PC. Okay, from there now we have brought it into the fetch register, and in the next cycle from the fetch we are getting it to the execute register. Also the contents of the program counter has been increased by 1, and that increased value, because once you do the addition out here, then that value will be brought, the new value +1 will be brought to the program counter. So this much part is going to remain here same for all the instructions. This housekeeping task for all the instructions will be the same out here, right? So what is going to change is this part, okay, execution part. Now if I have to load the contents of RY into RX, through RY through A, it is brought to ALU and also to the RX. Okay, now you might be wondering why to get it into ALU, right? So if you see, one more thing is written, it is 0 is also brought to ALU, right? So because what happens is, when we are transferring some data from RY to RX, the flags don't get affected of the ALU, but we might want to check, okay, whether whatever is the contents. For example, now when we are transferring contents, we must want to check whether, okay, whatever is the content has been transferred, whether it is 0 or it has got some finite value. So because maybe you want to use that for division, and if it is a 0, obviously you don't want to do it, right? So in that case, you want to check whether the item is whether the data which is brought, whether it is 0 or not, right? So what we do is we write another 0 to the ALU. So the contents of ALU will essentially be whatever is the data available in RY will be available in ALU also, and then we are giving another data as 0 to the ALU. So nothing would change. So the contents of ALU will remain Y, but by writing this additional command, okay, by what happens is all the flags will be updated, whether it be a sign flag or it could be a 0 flag, okay, whatever, parity flag. So all those flags will be enabled, okay, because only if you transfer between RY and RX, all the flags will not be affected. So you will not be able to take decisions, right? So you can't have conditional statements in your program. So just to check the the conditions, various conditions. So we have this this additional instruction of 0 also being brought to ALU, and this contents of RY also being brought to ALU. Okay, so that is how the load looks like. Similarly, you can have an store. Okay, what is store? The contents of RY. It is just here it is contents of RY being brought to RX. Here the contents of RX is brought to RY. So they are exact only the actually for a memory operation, load and store will be slightly different. For a register to register, they are almost the same thing only. Okay. Similarly, when I have to write an add, okay, between contents of Rx and Ry, so I can write I get Rx to ALU and Ry to ALU. The contents will be available in T1, which is again brought to RLU, so to RY. So the contents and RY will eventually get updated with the sum of Rx and Ry. So if you see here, this is not, because you are already doing an arithmetic operation, so all the flags will be taken care of. So there is no requirement of putting this 0 into ALU and things like that. So this is an straight away an add operation. So Rx is brought to ALU, Ry is brought to ALU. So you write an add out here, telling, okay, indicating in the flowchart that this is this particular box is meant for an add operation. So the contents are like, every time the contents of the ALU will be available in T1. So that also we saw, that is one of the rules. So from T1 it will be brought to RY. Okay. In the subtraction, again, between add and subtraction item, nothing is going to change, only that the top what we write here. So rest of the all, since it is again register to register, both are register to register. So everything, these things, they remain same. Only thing is, instead of add, we write a subtract here. So this is just the way of writing a flow charts. Okay, so the hardware engineer will know. Okay, so here the ALU has to perform an add operation. Here the ALU has to do an subtract operation. Okay, so this is how the subtraction code. So this we are only speaking about level 1. Okay, so once the level 1 is done, then we will see that how we can club these two if the spare bus is available, right? So you have to see the constraints also. So you can't bring any more instructions into here, because both the bus are being used here. Here only one bus is used. So probably we can think of getting this out, these portions into this box. So that is how from level 1 to level 2 optimization is done. Okay, the first and foremost is to write the level 1 instructions. Okay, so here here again we are writing level 1 only, but with memory reference. Okay, now here if you see here, so this portion again remains a common out here, housekeeping task, where from PC it is brought to ALU and AO and +1 to ALU, and then this is the contents of the given by the PC is brought to the instruction fetch, and from the instruction fetch it is brought into instruction execution, and the PC has been incremented by 1, and through T1 it is the contents of PC is being updated. So this again remains common to all of them. Okay, here. Now what changes here? Now if you see here, the the contents of an RX is brought to ALU, and to the ALU. Now in the previous instruction, it is assumed that the contents of of the from the memory location, because this is done for the next instruction. So it is assumed that for this particular instruction, okay, this has been done, already been done by the previous instruction, right? So the data is available here. Okay, from the memory, the data available in the memory, from where the data of that memory for which the addition needs to be done, that is already available in DI. So from DI it is brought to ALU out here, and RX it is brought to ALU. Now the contents of this is available in T1. So that is put into the DO, and we said T2 contains the address in memory operation. So from T2 it is put into AO. So this will happen. Now here if you see here, okay, we are not writing like here. If I go back here, when we learnt earlier register to memory operation here, right? So we are assuming that from RY, okay, this was brought into the AO register, and this data was brought from that memory location. So this we are assuming that this particular this contents of RY, like this one is, this entire operation is happening in the previous cycle itself here, right? Okay, and okay, that is happening in the previous cycle itself, right? Now if you see between add and AND, okay, these things, they remain the same, and for subtraction also. So this and these, okay, these three, they remain the same. Only thing is, this is changed from add to AND to subtract. Okay, so that is only a change which will happen in the execution sequence, because depending on whatever instruction we have, whether it is an AND operation, add, AND or subtract, so that needs to be written on top of the flowchart. Otherwise this is all the same sequence will be followed. Okay, so once you just have to understand what is happening with one particular instruction, then it is the same for all the instructions. We just have to change on top of the flowchart box and what is to be written out here. Okay, so similarly you can have for the memory operations and load and store also. So how it is done here? Now if you see here, from the we are getting some data from the memory into RX register, right? In that case from DI. Okay, DI. So we are assuming that in the previous instruction the data has already been brought into the DI. So through the bus B, it is being brought to RX and also being brought to T2, right? So this is the instruction where the load is done. Again, like, so we are writing these two additional instructions to check the contents. Okay, like from T2 we are getting it to ALU, and we are adding an 0 also. So that is to set the flag. So many a times, see if you have an you are adding say contents of memory. Okay, n number of data is available in the memory. You are fetching sequentially one each, and you are continuously adding it. Okay, so one way to do it is you specify the total number of bits which are total number of data which is available. Okay, sometimes it can happen that you don't know the total number of data available. That is also variable, but still you can say that if the last at the end of the data, if it is 0000, it indicates that there is no more data available. So in such cases, okay, how do once we make a loop, so this will help, right? So once you have once you get an 00 data here, okay, so say the contents of T2 will be brought to the ALU, and then you put a 0, then the 0 flag will get activated. So that is the reason, to just these are not actually loading the data. So here itself the loading action is completed here, right? From the DI through B, the data has already been returned to RX, okay, and T2. Now from T2 to bring it to ALU and 0 to also ALU, these additional instructions we are doing just to activate all the flags. Okay, not only the 0 flag, the sign flag and other flags, auxiliary flags, and all flags will get activated. So that will help in taking the next decision. So this is an additional thing which is written here, right? Similarly, if you have to store and data, right? And if you have to store and data, what do we do, right? So from RX you have to bring it to ALU, and to the also to the DO, and T2 will contain the address where the data needs to be returned. So that is brought into the AO register, right? So once you have done that, so the data will be returned to the memory address. Store means writing data into the memory. So these are the instructions. Again, then you are writing 0 to ALU just to set the flags. Okay, so this is otherwise here again here these things they remain the same out here. Okay, so these are some of the execution sequences for memory operand references. Okay. Now there's certain special instructions also, right? Pop and push. Okay, so if you see here a stack register, okay, this is how the lowest memory is on top and highest memory will be in the bottom. So you keep writing data one over the other. As you keep writing data, you keep decreasing the memory, right? And whenever we have to read the data, in that case we read the data and then again increase the memory. Okay, because the memory, this is the lowest memory, okay, and this is the highest memory out here, right? So and always the stack pointer will be pointing towards the topmost data. So in case I have to write a data, so since this is pointer is already pointing towards the topmost, I have to increase the pointer and then put a new data here. So if you see the push command, that is known as the push command. If I have to write the data, first from RY this is like, since the memory has been, I have to move the pointer towards the top, right? That means I have to decrease the count of the memory, because this is the bottommost will have the high memory count address, and this will have it. So I first I have to write a data, because this counter always points towards the topmost data, and that is the reason I do a -1 first. Okay, so the contents of RY is brought to ALU. I put -1 into ALU, and then the contents of that is put into the address bus, and then the new data is put into the DO. So that gets so on to the stack, the data gets return. Okay, new data. Similarly, when I am reading, so in the reading, when I am reading this data, I am popping it out, right? So in that case, it is already pointing out towards the topmost data. So I can straight away start the read operation. So I can put an RY into an ALU. So I do, but I am making, once I have read this data, I have to bring the counter to the I have to increase the value of the counter, so that now it is pointing, this data has already been read out, right? So now to point towards the next data, I write an +1 out here, right? So this is how, and push and pop commands will be written out here. Okay, so we'll stop out here. We'll take a break out here now. Okay, thanks a lot.